All right, let's have a look at this equation. It's Burger's equation, the inviscid Burger's equation, in fact. Let's say we've been told we need to discretize time with the Euler method and discretize space with a finite difference scheme, or a finite difference scheme. That means we've got this equation, which is continuous and whatever, and we're going to solve it numerically by applying finite difference schemes. One for time, we're going to use the Euler method for time, that's this component here. And then we're going to use our spatial component, that's this bit here, right? We're going to use the first order backward finite difference scheme. Right, so we'll have to figure out what these both mean. So let's look at the Euler method first. The Euler method is a way of handling ODEs, right? So if we think of this as an ODE in time, we can write this, right? So that's our, if you like, our time derivative on one side is this. It's just a rearrangement of the PDE. It's no big deal at the moment. What we know is the Euler method is for things like this. I'll just use different notation. Okay, so we know that the Euler method does stuff like this. We have fn plus 1 equals fn. So this is our new step. This is our old step. And this is our derivative at the old step. Okay, so that's what we've got here. We've got du dt equals this. So we can apply the Euler scheme. The Euler scheme is un plus 1, so this is our new time step. Equals our data at our old time step plus, oops, I need a dt in here. So I need minus delta t, because of the minus sign there, ux at time step n. Right, so, or present, actually, maybe present's a better way than saying old, because it's where we are now, where we're trying to get to. Okay, so once we've done that, we've actually done the first bit of the question. We've discretized time with the Euler method. We've now got a time-stepping equation. We need to handle ux. All right, this is the, because u is just u, right? We know what that is. We're not so sure what this is at the moment. So let's figure out this, and let's work out the first, let's work out what first order backward finite difference scheme means. Well, finite difference schemes, we want to approximate the derivative on a grid. So much like the Euler method for time, we're here. We're at, say, point J, and we want to use data surrounding J, the jth point, to approximate the derivative at J. we're going to go backwards, right? Because that's what the question asks for. We're told to use a backwards scheme. So we're going to use information from j minus 1, right? It's a first order scheme. Now, first order suggests lower is the lowest accuracy scheme you can possibly imagine, right? So we're just going to use 1 point extra to approximate our derivative. So what we're going to do is we're going to take our function u at j minus 1 and our u at j, and we're going to form up a linear combination and use that linear combination to approximate the derivative. In maths, I like to use the number of steps that I've gone as a subscript. Just makes things easier to track down. This approximates the derivative at the jth point. Okay, so now we can use Taylor series on our u to get this. Now, this is more effort than we actually have to go to. We could simply look these coefficients up on Wikipedia. Or if we're lucky, it'll actually tell us what the scheme is in the question. That would be even nicer. Let's assume that we don't have any of these things and we've actually got to figure out the method ourselves. That means we've got to substitute Taylor series for u j minus 1. We pretend we know this. We need to approximate this. So let's write down the Taylor series of u at let's say our coordinates xj. All right. U of x. Remember that the Taylor series is an expansion around this point. Oops. Getting a step ahead of myself. Du. Right, and I'm going to guess that because I've got a first order method, I'm only going to have to go this far. I'm not going to have to balance any second derivatives. All right. Xj minus 1 minus xj equals minus delta x. Right. We go one spatial step backwards. So let's stick this Taylor series now into this expression. This is our u. This is uj, right? I'm just translating the subscript and not writing the x out. And I'm not going to worry about the order 2 terms, right? So this is very much an approximation. I'm trying to approximate ux at this point. So I've got to form up my coefficients. So I could take this over the other side. Actually, I don't like that. I prefer to do it this way. I now need to balance my terms. I can balance this term because I have it on both sides. There's a 1 here. There's one of these. There's 0 of these terms. 0 uj plus on the other side. So I know that a0 plus a minus 1 has to be 0. So this term disappears. This term, however, well, it's clear that minus delta x alpha a minus 1 equals 1, right? Just balancing the ux's. That implies a minus 1 equals minus 1 on delta x. That implies, by back substitution in here, a0 equals 1 on delta x. That is ux at j is approximately equal to 1 on delta x uj minus 1 on delta x uj minus 1. Now that's kind of exactly what you'd expect from rise over run. Delta x is our run. We go from uj minus 1 up to uj, for example. That's our rise. That's our run. That's the expression we've got here. So clearly that's an approximation to our derivative. We take this expression now, this one here, and we stick it in here, right? That's the last thing we have to approximate. This thing in our box, I'll just note this is the first order backwards finite difference scheme. And if you go and look up the coefficients on Wikipedia, you'll be told that they're 1 and minus 1, and Wikipedia will tell you how to take care of the dx's as well, right? So this will agree with what you read on Wikipedia. We plug this into our semi-discretized problem. That is, we've already discretized in terms of time. UN plus 1 equals UN plus delta t ux evaluated at n, right? So obviously this is a product of u. We'll just say that we approximate this as UN ux at n. These are still time levels. Now we're going to plug in different spatial levels. So this is going to be at the jth point, at xj, right? So we've got to make this at xj as well. N plus 1 j equals unj plus delta t unj. Now we replace this with our finite difference scheme that we found here, where we write subscripts in time as well. Okay. And now it's just a case of rearranging for the nicest possible expression. This is what I'd use. Right, some people would write this differently, but this is the scheme applied to our Burger's equation. So we could code that up in MATLAB, loop in time and space, and we could get an answer. It wouldn't be a very good answer. This isn't a particularly accurate numerical scheme, but that's how we go ahead and apply a couple of numerical schemes, namely the Euler's method and the first order backwards finite difference scheme, to a PDE.